Okay, so welcome, and welcome to today's session, Tuning Solr and its pipeline for logs. I'm Rafał, and here is my colleague Radu from Sematext. We're a company that provides professional services, log analysis software, and metrics monitoring software. But that's not very relevant for now, right? What we'll talk about today
is so we're going to talk about how to use Solr for logs and how to tune it and its pipeline. So we're going to look first at the kind of cluster level overview where you're going to put your nodes and shards, and then we're going to dig down to Solr settings, operating system settings, hardware, and then finally we're going to look at pipeline patterns, like where you want to buffer parser data on its way to Solr.
So the biggest advantage you can get and the biggest kick in indexing throughput you can get out of Solr is actually divide your data. So first of all, let's talk about time-based collections. If I'll say index, just say this is not Elasticsearch. So basically what you do, for example, let's assume that we are indexing logs here to our collections, and we have you heard the talk today, you are say, okay, I'm going to index the logs. So what you do is you go today to the hotel room to go tomorrow and say, I'll create collection for tomorrow and start indexing my logs. So I create a single collection. And then when the day comes to an end, you just create a new collection, switch the alias, or your log shipper knows the naming of the collections, and you start indexing to the second collection that you created. The benefit of it is we are actually allowed to skip some very expensive parts of Solr indexing process. One of those, which is merging. So by limiting the data somehow, we are allowed to avoid expensive mergers, like for the large segments, and still keep the throughput under control. So we can actually provide ourselves with some visibility of what hardware we need to process the data and process the logs that we are going and we would like to have indexed. And the indexation continues, right? When the next day happens, we create another collection, and that what comes with it. Another nice thing about those splitted data between the collections is that we actually can avoid delete by query. Why is that important? Because, as you know, Lucene segments are immutable. That means that wherever you are deleting the data, it just creates a single small pointers that these documents are deleted. They are not physically removed from the index until a merge happens. And again, merges are expensive. They require a lot of I/O operations, which we would like to avoid. That's why deleting the whole collection in general, just by dropping the files on the file system, is way more efficient than doing a delete by query or delete by ID. Of course, that also allows us to lower down searching footprint, because if we only do searches on a certain data, like if we are interested only in the newest data, like for the current day or 24 hours, we can limit the searches to a certain amount of collections instead of going through all the data we indexed, like all the logs till from the day we started indexing, basically. So that's why this is important. However, there are things that can cause problems with it. Imagine that we are in a commerce shop that logs the client behaviors, behavior of our applications, what was sold, and all that kind of information. During the Black Friday, as an example, you will get lots and lots more traffic, usually, and you'll get the collections uneven. Then we have the Saturday, Sunday, which are probably going down with the amount of clients that are coming into the users and searching and doing all this, what our application is capable of. And that's when things, again, start to not scale very well. Because if you have a spiky behavior, then you really need to over-provision to be able to provide an acceptable query performance and indexing throughput to have that done. Because of that, there is a way to actually improve the whole throughput. And instead of using a daily, monthly, or hourly collections, we will want to go with something else. Octi is very worried, by the way, because the daily collections are suboptimal. So what are we going to use? Actually, rotating by size. This is one of the things that can give you an acceptable information and insight of what your hardware is actually capable of. When you know that your servers are able to provide with a given amount of document on a collection, let's call it like 10 gigabytes, 100 gigabytes on your hardware, with an acceptable query performance and and this is the limit for your throughput. Basically, you can't index documents fast enough to be near real time, as close as possible, then it's time to roll the collection and create a new one. So when we hit that limit, the size limit, we roll, we create a new collection, just like we did with the time-based collections, like with daily ones or with monthly ones. We just roll back, switch the alias to the new collection for write, and we write to another collection. Right? Again, the same procedure happens. We just do that collection by collection, and we even the data load. The idea behind this is, again, to flatten down the spiky behavior, because if we know that with a given throughput, we can get a maximum throughput of our data till a certain size of the collection, we can limit by that size. The idea is not to be very precise. It doesn't really matter if it's +5 or -5%, right? If we are close to the limit, somewhere around that bucket, we just roll the collection to a different one and go from there. Again, predictable indexing and search performance, as we already mentioned, and fewer shards. Why? Because sometimes, as in the example with the Black Friday, one of the collections was very high, it was very large, and the others were tiny. Here, if we split by size, we are allowed to actually merge those tiny collections together to a given size, and that's when, again, we gain by reducing the number of shards and reducing the number of collections, which can be deadly for your SolrCloud because of the amount of data that was needed to be held in Zookeeper, about the collection state if you are running on cluster state if you are running on 5x, or per collection state if you are running on 6 already, right? That still needs to be written. All the collection informations, all the shards needs to be written down into Zookeeper. If we have less, then less memory and overhead is needed. When it comes to searching, though, we need to know where the data lives. Why? Because we need to query appropriate shards for the data. With size-based collection, we don't have a clear boundaries where the logs are living. We can have logs living in multiple collections from the more or less the same time frame, right? That can happen because if we put logs one after another, we can just switch collection, and some logs from the same hour may live into two different collections. That's where we need to, for example, use facets and just write some cache to the application that reads the logs and say, OK, collection with the given name has boundaries from min time to max time. And that's where we know if someone, for example, chooses a 1 day worth of data, we just use the cache or use facets to first get the idea about which collections have the data, and then search on that particular collections. Of course, if we are only interested in the recent data, no need to search. We can just use the recent collection and just, for example, if we are only want to do a live tail functionality, like show the newest logs, then it's very simple. You sort by timestamp or the time creation date of a log event, and then go and use only the newest collections. This is how you can actually deal with it. And the general conclusion for that part is that size-based collections allow us to handle spiky load better, right? We can flatten the load, we can control that, and be able to predict what our environment is capable of, which is crucial in that kind of situations, which we will get to a bit later when talking. Of course, this is not the only thing we can do. Whenever running into time-based data, there are a few assumptions. One of the main assumptions is that your data is not changing within time. If we indexed the logs from yesterday, we probably won't update them, right? There will be more or less static. Some updates can happen, but it won't be as intensive as the indexing for the current day. So the idea behind here is to divide your cluster into multiple tiers. The simplest solution is to have so-called cold and hot tier. The hold tier is the one that handles the indexation and near real-time searches. So the recent data, the data for today, or whatever amount of time you need to be able to search in a near real-time manner. And those servers are usually the ones that need many IOPS, so many very good disks and good CPU. So you need CPU because indexing is CPU intensive, and you need I/O because segments will be created, merges will happen. Ideally, SSDs here. If no SSDs, then write 0 with the spinning disks. We'll get to that as well in the later part of the talk. The second part of our architecture is the cold cluster, is the cold part of the cluster, which means we can slightly lower down or choose a completely different machines here and account for two things. First of all, we need to account for the memory that segments will use and that Lucene will use statically for the data that is there. Apparently, I'm not sure if you're aware of that, but just for you to know, Lucene needs a static amount of data for each of the opened collections. And it is the amount of data usually is from 0.05% to 2% of the size on the disk. But there's are assumptions that we've seen during professional services consulting. And the idea here is that the cold cluster, cold nodes, sorry for that, won't be queried as often. This is more of an archive or for building up reports that cover more data than the near real-time requirements for our system. So if we were like, for example, if we keep our data for 30 days and we are only required to search on the recent data like for the 3 days, we would keep 3 days of collections on the hot tier and the rest of that on the cold tier. So the hot tier may do the most expensive operations while the cold tier is more of an archive. We like tiered clusters because they can be cost effective. We can lower down, we don't need to buy the same hardware for hot and cold, and we can lower down our costs. The performance is also nice because we have fewer shards, so less overhead. We are allowed to dedicate the CPU processing memory and I/O to a different purpose than just indexing on all the servers. And finally, long-running searches won't slow down your indexing because they will be probably the ones that will run longer, will be executed on the cold cluster, cold tier, which is actually not doing any indexing, so the hot tier won't be affected by that.
Okay, so a bit about hardware now. I'm going to talk about AWS, but I guess a lot of this stuff can be translated to other environments as well. So our instance of choice for the hot tier is C4, which is compute intensive. The problem with it is that it only has the EBS storage, so the network kind of based storage. If you want better latency and throughput, you can go with C3 instances, which are somewhat more expensive and have a tiny bit less CPU, but they do have some local SSDs that you can use. However, you're normally gonna outrun like the amount of data that you can store in them. So then you'll still need to add some more EBS to those C3s. But even if you do that, then you should be better off than with the C4s in terms of performance, because you can use the local SSD as a cache. And there's two ways you can do the cache. You can do it like read only. So this is I'm talking about LVM-based cache. So you can basically mount use the SSD. You can mark it as a cache for the EBS, which will be larger. So you can use this as a read time cache, so the writing would be synchronous, or you can say cache mode write back, and then writes to EBS would be delayed a bit, so you get a bit more throughput. But this configuration will be more expensive. For the cold tier is more of the same story. It depends of the balance between how much money you want to spend and how much performance you will get for that. You can use D2 instances, which are like, let's say, storage intensive. They have lots of RAM, but also lots of spinning disks. If you want a bit more throughput and latency, you can go for M4s. These are well-balanced instances, are kind of like C4s, but with more memory. and come EBS optimized, just like C4s. And then you have the flexibility of adding the a smaller or larger EBS on top of that. The i2s are the most expensive and also the best because you have the big local SSDs. These are like equivalent to D2s, but you have local SSDs instead, which are smaller than the spinnings you get on D2. So you'll need more of those. If you end up using EBS, and I'll have a separate slide for EBS, but for the instance itself, you can choose for it to be EBS optimized, which means it will get a separate network interface for talking to EBS, which will make for better throughput. All instances can have, not all instances, but most kind of later generation instances support enhanced networking. This is like a driver level thing of the network, the way it communicates to the hypervisor. But you need a recent enough kernel to be able to support that. So for example, Red Hat 6 doesn't quite get that, but with 7 you do. And finally, to get some of those instances, so that like the C4s and M4s that I mentioned, you need to be on VPC. So if you're on EC2 Classic, you don't get them. Okay, EBS. It's quite a busy slide, but bear with me. So basically, the more throughput you need, the bigger the instance, the more throughput you get, up to a certain limit. And that limit is 10,000 IOPS, or 160 megabytes per second. So you really want to stay under that 3 terabyte kind of volume size at which you don't get any more IOPS. You can also get, based on the size, you get some credits that you can use to get up to 3,000 IOPS. And because of that 3,000 IOPS limit, this only applies if your volume is up to 1 terabyte. So again, if you don't need super large EBS, you're better off having smaller ones because then you'll get a bigger burst. There's the tendency of having more smaller volumes in RAID 0, so you get more of that bigger burst. But the problem is performance for EBS, and I'll get to EBS types too. I'm talking about general purpose SSD EBS here. So the performance of that isn't guaranteed. So the problem is if you have, let's say, four of those in RAID 0 and one of them misbehaves, then all the RAID will suffer because they will all wait for those writes to go to the slower disk. And I mentioned there are multiple types of EBSs. There's the most expensive one is with provisioned IOPS that does have guaranteed throughput. But the problem is it's super expensive. We have yet to find a logging use case where this works. And spinning disk-based EBSs, these tend to be too slow for most logging use cases. But if you have very rare long-running queries, those might still work. So to try and summarize all these things, we prefer C4s for the hot tier because they're almost as fast as the C3s, but we get away with less money. M4s provide this good balance, and we can provision as much EBS as we need, and they also scale up to like 10XL, which is a pretty big instance. And with EBS drives, we try to stay under 3 terabytes, and we don't really care of putting more of them into RAID 0 because of this thing that one of them may have worse performance for a while. Moving on to the operation system, obviously you don't want your instance to swap, so you need to disable that, I guess. Disk scheduler, this depends on what kind of drives you're using. The default on Linux is completely fair queue, which kind of serializes writes. So this is good for spinning disks, but if you're on SSDs, you'll need to use either deadline or no op to get more IOPS. Mount options, you can skip writing access times for files in directory, and you can also make the journal not care so much about the writing order. Of course, this will, it's possible to lose data in this case, obviously, but that's what replicas are for. And if you're on bare metal, you might need to check for other things. For example, the CPU governor, which takes care of power saving, actually by scaling the CPU frequency, and transparent huge pages, which allows the operating system to address bigger chunks of memory with one address. That is often, like for many data stores, you see the recommendation that this should be disabled. The funny thing is, it's enabled on most operating systems by default, on most like Linux distros by default, but the number of allocated huge pages is 0, so that's effectively disabled. But I think it's worth checking to see if it actually is enabled or disabled for your use case.
So okay, we went down to the operating system specifics, to the disk, and now let's get back to Solr for a bit. So all those things that you need to configure in Solr to make it perform better or worse depending on your use case. So first of all, the 2 auto-commit settings. The hard auto-commit, which is all about flashing the data to the disk, right? So do it as least as possible. It will flash the data, create the segments. Remember, this can cause merges, so expenses of operation. One every 32nd minute or every few minutes, depending on how much data you are actually indexing. Auto-soft commit, all about data visibility. If you need your logs to be visible right away, 1 second, 5 seconds. If you can wait a bit more, 30 seconds may be nice. The idea behind this is we did some tests some time ago, and let's say that we had a baseline of 100% of indexing throughput with 1 second of auto-soft commit. With 5 seconds, we got the improvement to throughput by 25%. With 30 seconds, it was 75% compared to the base throughput, which was calculated at 1 second. So you see the difference. The idea is that going above 30 seconds usually doesn't make sense unless your hardware is really, really stressed out. So auto-soft commit, visibility. Hard commit, durability, and flashing the data to disk, clearing transaction log. This is also not the only way you flash the data and actually make the segments to appear on the disk. Another thing is the RAM buffer. So the higher the RAM buffer you have, the more throughput you will have, because Lucene will write the actual data to memory. And then if the buffer is filled or auto commit happens, the hard commit, the data will be flashed then. Less flashing, less segments, less merging, faster indexing. Then, as merging is expensive for indexing, facets are expensive when it comes to searching. Not only because they need to get through the data, but also because they need to uninvert the inverted index and basically put the data in memory. If we want to avoid that, go for doc values. Dedicated data structure calculated on index time, which Solr can use to actually calculate facets without going into memory and uninverting the data in real time. That saves garbage collection issues, less memory usage, and basically faster facet queries at the cost of a slightly slower indexing speed and a little more index space consumed. Also, if you use doc values, do not store the fields. You can retrieve them from doc values. Omit norms, frequencies, and term positions. Why? Because when dealing with logs, we usually are interested in sorting by timestamp, right? So most of our searches will be sorted by timestamp. Not a lot of logs will have exactly the same timestamp because it's up to millisecond. So really, the relevancy doesn't matter that much. If we will find the documents that we are interested in, for example, the ones that have severity error, that's more than fine to sort them by timestamp, so when they did occurred on our systems. Finally, don't store the catch-all field if you use one. The catch-all field, you basically copy all the other fields to use a field to search on the default field, so you don't need to care about the field names. If you use such a field, don't store it. It doesn't make sense. You usually copy that data from other fields, so you probably have that fields already there, either by using doc values or already stored. And again, getting back to those merges, they're important because they do affect performance of indexing, basically indexing throughput. merges are the heaviest part of indexing. Search facets are the heaviest part of searching. And how to combine them both together? You'll probably heard sometime in the past that your searches will be faster if you will have less segments. Probably, how many of you heard that sentence? OK, some of those. And that's true, but for full text searching. While doing facets, Solr just goes through all the data sequentially, and we really are not limited by the number of segments, but the size of the data. That's why we can relax the merge policy slightly and allow ourselves to have higher number of segments at the benefit of higher indexing speed in that case. That matters. So what we can do? We can actually tune 3 parameters there. First of all, segments per tier. The higher segments per tier, the more segments are allowed to be created. So whenever more segments are allowed to be created, which means Lucene will do less merges in these background threads that are fired up for merging, which means higher indexing throughput because of less I/O to be used. When we are tuning the max segment per tier, we are usually going up as well with max merge at once, which means how many segments at once can be merged. Do not go as much up as with segments per tier, and that will smoothen out the I/O because of less segments being combined together at the same merge time, and it will smoothen this merge process in time, making your I/O and merges process more predictable. Again, better scaling. We can predict and account for merges when we scale our environment. Finally, max merge segments in megabytes allow us to tell how large the segments could be in size, in total, per segment, of course. So the larger segments won't be combined. Imagine that it's easier for Lucene to merge 5 segments of 100 megabytes in size than 5 segments, 5 gigabytes in size each, right? That requires reads, that requires writes. So again, writing and reading 25 gigabytes is more work than writing 500. And one thing that I wanted to mention, that max merge segment in megabytes actually won't make your number of segments larger, because instead of focusing on those larger segments for merging, Lucene will focus on the smaller ones, which Radu will actually show you now.
Yeah, so we did some tests. Here are some juicy numbers. Basically, when we went from the default of 10 segments per tier to 50, that's when we got about 10 to 15% more indexing throughput. In both cases, we actually did more than just 2 tests. We got this behavior that indexing throughput was high, and at some point it started dropping quite abruptly. The way we actually tested this was how much indexing throughput can we squeeze in a shard before, while still being under an acceptable query throughput. So, actually not throughput, but latency. That, and yeah. So another test I wanted to show how what Rafał just said, that when you're lowering the max segment size, so the default is 5 gigs, we lowered it to 500 megabytes. And what we saw is with similar indexing throughput, we saw that we had fewer segments and the CPU usage was smaller. So we were more efficient in indexing. We have all the tests in GitHub, like the JMeter test plan. We have more screenshots from the tests, so you can basically replay those tests. So basically, yeah, you can relax your merge policy and get more indexing throughput and less spiky search performance, because if you're not doing those big merges by reducing the max segment size, then your searches will be more consistent. And that, I think I covered it all. Okay.
Yeah.
Optimizing, this is something you may feel like doing for those collections that are done, but for most use cases we found out that doesn't actually help. It's not helping so much in terms of search throughput, especially if you're using a lot of facets, And if your data velocity is quite high, then you'll need to spend a lot of time doing these optimizations, and then that will take a lot of CPU and I/O. Oh, so I'm going to stand here now. Next I'm going to talk about the indexing pipeline, and there's a bunch of things that you need to worry about, like shipping your logs to Solr. You'll probably need to buffer them along the way. You need to choose which protocols to use along the way, whether you want to route to other destinations too, and whether you want to parse unstructured data if that is needed. So buffers, you will need buffers for two reasons. One, availability, like if Solr is down or falls behind, you need to be able to replay those logs from somewhere. And performance, because having a buffer allows you to batch multiple messages in one request, and this is absolutely necessary to get high indexing throughput. So there's a bunch of ways to buffer. Obviously, you can buffer on disk, in memory, or some shippers offer a combination of both. But you can also choose on whether you want to have a centralized buffer like Kafka, or you want to have a log shipper that buffers on every machine that is logging. There's also a matter of where you do the processing and whether you want to support multiple destinations or not. And this is where different log shippers have different approaches. So something like Logstash, for example, will have a small buffer before processing, so it can process things in batches, and then it can send data to multiple destinations. The problem with this approach is that if one of the destinations falls behind or it becomes unavailable, then the whole pipeline blocks waiting for it to become available again. So some other log shippers approach this by saying, okay, I'm going to do the processing on the input side, and then I'm going to send it to different buffers, one for each destination. This solves this problem, but if processing is expensive, then you're basically putting pressure further back the pipeline. If you use something like Kafka, then each consumer can have its own offset, so basically processing can go asynchronously. So this, I think, solves this problem better, and you're doing all the processing on the consumer. Other shippers, for example, our syslog uses this kind of mixed approach where input goes into a buffer, then you can get to do some processing and fan out to other buffers to different destinations. So this gives you a two-step process where you can have some processing on all the data, and then depending on where you're going to send it, do some additional processing. So I'm trying to sum up some top picks here. So if you're just sending, so if you want to go for something simple, just send your data to Solr and maybe to some flat files. Then having a lightweight log shipper on each logging machine that can do some buffering, I think that's going to be the better approach, because then you can, as you add more logging machines, then you're basically adding more capacity for both processing and buffering. If you want to do something custom that's constantly changing and don't want to redeploy, you don't want to care about these logging machines, then you want to have something central like Kafka, and then control your stuff through consumers. To parse unstructured data, this might or might not be needed. Ideally, you log in JSON, because parsing JSON will be faster than just doing regex or whatever. Also, when your logging format changes, then you can maybe just have to adjust the schema in Solr, but you don't have to change your pipeline. But sometimes that's not possible, so you still need to parse like third-party application logs and stuff like that. And here you have two options. You can use regex-based parsers, like what Logstash does with Gheorghe. These are flexible to use and easier to build because regex is so flexible, but you lose on the performance side, especially as you have more parsing rules, then it needs to go sequentially through them. Though different log shippers have all sorts of tricks to try and evaluate less of those rules. The alternative is to use a grammar-based parser, which can build like a parsing tree on startup, and then basically can give you consistent performance no matter how many parsing rules you have. You need to decide what happens when the buffer fills up, because you basically have two options. You drop data or you wait. And waiting is often not an ideal thing. You can drop data at the shipper level, obviously, but probably it's better off to drop data at earlier in the pipeline, like if all the buffers fill up. And there you have to check, depending on where the application logs, things like what happens if the log I'm writing to gets rotated, what happens if the TCP connection gets dropped, what happens, or if I'm logging through UDP, is the destination able to process data as fast as I'm sending it to it. So we try to make this flowchart to simplify the options. Basically, if your logging isn't critical, UDP is a good choice, assuming that the next hop can process data even during spiky times. If logging is critical, then you need to pay for this reliability either with I/O or with memory, because yeah, you can write to files and then make sure that you don't run out of disk, or you can write, for example, to a Unix socket and then make sure that you have a local log shipper always available for reading from that socket, and also being able to drop logs if its buffers get full, because otherwise, with actually all Unix sockets, the call is blocking. So if the other side is blocking, you'll lose data. It's not, you don't lose data, you'll block. Protocols, UDP is pretty straightforward. TCP is reliable at the protocol level, but you can still lose data that's in the operating system buffers, because the application gets an acknowledgement once data is in the buffer. So if you want some more reliability, you need something that acknowledges at the application level. And depending on the log shipper, you have a bunch of options. Trying to summarize all these possible combinations, you can guess there, I guess, hundreds. If you want something simple, you can just go ahead and like log to the local socket and have some lightweight log shipper like rsyslog do all the processing and the buffering for you, and then send data to Solr. If you want to have something more involved, then you can log to a file. You can have again a lightweight log shipper like FileBit to send data to Kafka, and then you can do all your stuff in a consumer or multiple consumers.
So basically, that was all. The whole talk was pretty much about, about conclusions. If you would like to talk about performance to us, have any questions, talk about those pieces together, those Legos of the pipeline combined together, poke us on Twitter. We're here at the Sematext booth with Sematext. Come, talk to us. We'll be happy to answer your questions, talk to you. We probably don't have much time right now,
we have a couple of minutes, right?
Thank you very much for attending the talk. Hopefully you get something out of it. And once again, if you want to reach us, we're here for the whole conference, and we'll be happy to talk to you today. And we'll invite you to our second talk tomorrow about Solr and Docker. Thank you very much, and enjoy the rest of the day.